Welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one focuses on the basic principles of mechanics and in particular on Newton's laws. Let's begin. The first law is that a body moves with a constant velocity in a line or remains at rest if no resultant force acts upon it. That may appear either very obvious or really quite hard to credit. Certainly when it was first formulated several hundred years ago, Newton was making a revolutionary statement, the idea that things would continue in motion if no forces acted, when to some extent the evidence of the world around is that everything that's in motion eventually stops. It was an inspiration to realise that that's because forces are acting upon whatever it is that's in motion, and if there were no forces, then motion would continue uniformly, that is in a straight line or a continued state of being stationary. A revolutionary thought then at the time. So now let's look at that's a statement in mathematical terms that the total vector sum of the forces is 0. Now the next thing concerns what happens if there is a force. If there is a resultant force, that is to say the forces don't add to 0, then the response of the body is that it accelerates in the same direction and in proportion to the force. That defines acceleration, and it may be called the equation of motion, what results. So instead of sigma f equals 0, this time you have sigma f is equal to the mass times the acceleration. And you see here that mass is essentially the constant of proportionality. So the physical concept of mass corresponds in maths to the constant of proportionality in this equation. And if you put that the sigma f is 0, we go back to the original situation where there is no acceleration, which corresponds to a constant velocity, or the special case, 0 velocity. Now the third one is the subtle one. Every action produces an equal and opposite reaction, as it is traditionally been stated. Now what that's saying is as simple as that if you have the idea of a tug on a river towing a boat, the rope between them is tight, and from the point of view of the tug it feels a force trying to slow it down, pulling backwards in the direction of the barge behind it. From the point of view of the barge you feel a forward force pulling you towards the tug. Now those are manifestations of this phenomenon that Newton's third law states, namely that to every action there is an equal and opposite reaction, or in modern day terminology as you see it on the screen. So now let's look at some examples of how this works. We've got here two walls and a ladder. It's helpful, I think, when drawing force diagrams to draw gaps between bodies which are in contact. So that looks a bit unrealistic, but the reason for that is it helps to make clear what force acts on what, as we'll see in the next diagram. So here, sorry, that jumped. Here we have the force diagram that we're asked for, and you'll see that you've got a force from the wall acting on the ladder. Now there would be an equal and opposite reaction of the ladder on the wall. There would be a force X there, and that would make a mark in the wallpaper, to say the least. It would be the pressure of the ladder, that's what we would call it in everyday terms, but it's actually the equal and opposite reaction. Now similarly at the floor, the carpet will be rippled to the left because the floor would be feeling a force to the left, which corresponds to the F, which is maintaining the ladder in position, and which we denote as friction. There'd also be a dent in the floor. If it's a tile floor, you probably see a mark when you take the ladder away that corresponds to the equal and opposite reaction downwards, that would be the R. Now by showing this gap, we make clear what acts on what. This X acts on the wall, this X acts on the ladder. Now we've got some analysis here. If you use Newton's first law, that's what that cryptic reference means, Newton 1, resolving to the right, considering the forces as vectors and taking the components which are parallel to the horizontal, then reading across the diagram, R contributes nothing, F is positive to the right, x is negative to the left, so f minus x equals 0. That boils down to saying, of course, that f equals x. And similarly, if you can take resolving vertically, so that would be with a vertical sign there, then taking upwards as positive, you'd have r and minus mg equals 0, so you get r equals mg. Now let's look at the situation for a smooth floor. Now again, I'll use the gaps. So looking at the smooth floor, we could put in the same complement of forces on the wall. I'm not going to do it because it's not relevant to the analysis, but it would demonstrate the way the Newton's third law works in this context. Now this time, if you resolve horizontally, you'll see that you're trying to balance an x against a non-existent friction force to the right, and that therefore is impossible. So you've got a situation which can't be in equilibrium. Now that's really quite a practical point, because if you have a ladder which you're standing on a polished, highly polished floor, while the ladder's in position and there is no weight on it, you probably can get it to stand. There will be a bit of friction even from a polished floor. But as soon as you start to put serious weight on it by putting somebody climbing up it or standing in the middle, or the ladder is indeed itself heavy, it simply won't stay up, because from a polished floor there is almost no friction, and if we idealize that, as in this case, by saying there is no friction, you see that it can't be in equilibrium. So that's actually quite practical, despite the fact it seems somewhat contrived. Now let's look at a car with a given mass and a driving force, and this experiences a resistance of 1400 newtons. So we have to find its acceleration. Now this will depend on drawing a force diagram to see what's happening. We'll begin by considering the motor car as a particle. So here's our particle diagram. Now again, I've drawn it not in contact with the ground, so that I could, if I wanted to, show a vertical force which is equal and opposite. That's the reaction, and it's equal and opposite to the weight downwards, which in this case will be 900 G. So those notional, well, they are there, but the thing is, we're only interested in the resolving horizontally, so we can get away with not putting those in, but they're there for completion. Now if we resolve Newton's second law using F equals ma, taking positive to the right, we have the 3200 and the 1400 acting to the right and to the left. I should have put newtons on there, shouldn't I? How naughty. You've got the 3200 to the right and the 1400 to the left, and you have the mass times the acceleration, and the mass is 900 kilograms, and the acceleration is given on the diagram as a meters per second squared. If you introduce a letter, as we're doing here as a convenience for something that we want to find, putting it on the diagram is much easier than writing a sentence saying let the acceleration be a meters per second squared. We need to do one of the two, but the diagram is the easier one. So solving that equation for a, we get a equals 2, and our conclusion is that the acceleration is 2 meters per second squared. That question illustrates in a nutshell the essential steps of using Newton's second law. You draw a force diagram and then you analyze it in that way, and that gives you a clear and easy answer. Now let's look in the same spirit at the way we deal with someone in a lift. So we need to draw a force diagram for her and find the reaction force from the lift. Now again, we represent her as a particle. She's got a weight acting upon her, 48 G, and the reason that she doesn't go shooting down the lift shaft is that the floor is exerting a reaction force upwards on her, which I've denoted there by R. And we've got an acceleration of 2 meters per second squared upwards. Now this reaction force R, you may be tempted to think it's the same as a 48G. Well, it would be if the lift was stationary. But if it's not, in order to have an acceleration, that R must be bigger than the 48G, and it's Newton's second law which allows us to work out what it would have to be. So if we do the analysis F equals ma from Newton's second law, resolving vertically, then taking upwards as positive, we've got two forces, R and minus 48G, and that has to be the mass times the acceleration, 48 times 2, the acceleration also being upwards. So if we solve that using the usual value 9.8 for G, we'll end up with 570 approximately, so we can say that the reaction force is 570 newtons. Now notice in this equation here that this is really saying that the reaction force is greater than the weight. Now that's at one level intuitively obvious, but the other is that it comes from the analysis, and it shows that from the point of view of her legs, which are the immediate agents of this force, then she'll have the sense of being much heavier in proportion to the increase in velocity, the rate of increase of velocity, the acceleration. So that accounts for that physical sensation in the legs, that you a sense that you're being compressed, which corresponds to feeling heavier. Now if you make that force very large, as it would be in a spacecraft, you have the problems of just how much the human body can stand by way of that excess, and that's a major issue when designing a spacecraft. From one point of view, the greatest possible acceleration is necessary, or will be ideal, but from the point of view of the tolerance of the human body, there's a limit to how much we can expect it to cope by way of that compression. Now let's look at the corresponding case where she's moving with a constant speed. Now if it's a steady 15 meters per second, that means there's no acceleration. So in the F equals ma equation, you're going to end up with a 0 on one side. So it's immediately obvious that R must be equal to 48G. That's almost a statics problem. Almost, not quite. 48G. So taking the G as 9.8, we can get an answer for R from that. Now, if we consider that she decelerates, you've got a -3 on the arrow here. That could, in some ways that's somewhat perverse, though it's totally correct. You could also show the arrow going downwards with a +3, so long as you remember to interpret that as -3 when you consider that positive is upwards. But the analysis is much the same. We have the forces on the left, taking account of direction, and we have the mass times the acceleration on the right. And so again, solving this and using the usual value for G, we end up, with the use of the calculator, with 330 approximately. So the reaction force in that case is 330 newtons. And this smaller reaction force in this case makes her feel lighter. That's why you get that sinking feeling when the lift sets off. That concludes this video presentation. The next in the same series on basic principles of mechanics focuses on the so-called Suvat equations.